Hi everyone, welcome back. This is part two of our discussion about cycloalkanes relating to chapter 4 of the McMurray Organic Chemistry textbook, which is um, available online now from OpenStax. Uh, the link to the slides I'm going through here is in the comments down below in the description, so you can find that and follow along. When we left off before, we had talked about alkanes and conformations of alkanes in the open chain form, and just started to touch on cycloalkane conformations. So this discussion is going to pick up where we left off before. And what I wanted to remind you about is that we have, there we go, we have this discussion about energy. So everything that we're talking about has to do with the angle of the ring as well as these two kinds of strains. So the more sharply constrained the angle is from the normal tetrahedral carbon conformation, the higher the energy that molecule would be. And the more bonds line up with each other, if we think about Newman projections, these would be eclipsed bonds, the higher the torsional strain will be. Likewise, atoms connected to those bonds, the larger those are, the more steric strain we will have. So obviously hydrogen would be the smallest atom that we could have. That's kind of our baseline for steric strain. And then anything larger than that would increase the strain on that molecule. So as we go forward here, we can go back into the late 1800s here, and people were looking at different molecules and came to this realization that there were lots of 5 and 6 membered ring structures in nature, but not really a whole lot of smaller ones. And the sort of first prediction of this, or first explanation of this, was ring strain theory, that basically hypothesized that the more deformed, the more compressed from a normal tetrahedral 109-degree angle the ring was forced to be, the sort of less stable it would be, the higher in energy. And so, of course, if we look at the smaller rings that we could see, cyclopropane, in order to get this triangular structure, we know the inside angle of a triangle is about 60 degrees. And so that's about 49 degrees separated from the, otherwise open chain carbon tetrahedral angle. Similarly, cyclobutane is restricted, but less so. Cyclopentane and cyclohexane are reasonably close to that angle. And so, by all expectations here, we would have said that cyclopentane should have been the lowest ring strain. And that's if Bayer was actually right. He was close. But remember, these structures that we're drawing here, these geometric figures, are drawn on a flat page. Turns out that molecules can bend a little bit. As we talked about last time, there's a little bit of twist that's available. And so when we actually go ahead and look at the ring strain energy, and this would be calculated by measuring the energy released when we break open that ring, we can see that yes, 3 and 4 are high energy, but 3 should be much higher than 4, and it's really not. Also, 5 was almost the ideal tetrahedral structure, having a 108-degree angle in the pentagon instead of 109. So it should be basically 0, and the 6-membered ring was sort of stretched a bit, 120 degrees, relative to that 109 degree that would be perfect. And so those smaller ring shapes don't quite fit what we'd predict from those flat geometric figures. And then likewise, what we see is that 7s are about as strained as 5s. 8s, 9s, 10s, and 11s are a little higher. 12 seems to be a sweet spot. 13, and then by the time we get to 14, the ring strain is basically negligible. And it turns out that this is really because of the flexibility of these molecules to pucker and twist and not quite form these flat structures. By the time we get up to 14, the molecules are so large that they effectively behave like an open chain alkane. They can twist and bend quite a lot. But if we look at these small ones and we focus in on trying to understand what these 3 types of strain are about, angle strain I think is pretty easy to understand. When we look at torsional and steric strains, these are really easily visualized with Newman projections. And so here's our cyclopropane flat triangle structure. Notice our 3 points do define a plane, and so we can't really pucker this one at all. If we were to look at it from the side, we would see a Newman projection that looked like this. Now, notice in this kind of a ring-shaped Newman projection, we see this typical Newman here with the 3 lines in the dot representing our front carbon. In this picture, that would be this carbon right here, right there. And then that back carbon would be the one drawn at the top of this picture. So the view that we're looking at would be with our eyeball here looking that way. And so what we see here is that with that flat triangle in the plane now of our viewpoint, we see that all of the bonds are eclipsed. And so we see this eclipsing here. If we were to change our perspective and look along any of the other two sides of this triangle, we'd see the same thing. This eclipsed conformation can't be avoided in cyclopropane. And so yes, it has a tremendous amount of angle strain. It does also have torsional strain from those eclipsed bonds. And the steric strain, it is eclipsed. It's sort of the best it could be with hydrogen. If these were bigger, okay, let's imagine that these were methyl groups now over here. So a 1,2-dimethyl cyclopropane. Now that would have a higher steric strain yet because these groups are larger and there's more of that atomic interaction. And so we can see that if we look at the costs of some of these things, this very sterically strained tetramethyl cyclopropane here. These are prices I pulled from an old Sigma Aldrich catalog I had laying around, but regular old cyclopropane was about $200 for 25 grams of the stuff. This was about $2,500 for 25 grams of the stuff. So you can see that increase in cost as a very indirect measure of the decreased stability. Now, if we go and look at cyclobutane, rather than this being a perfectly flat square, if that were true, then when we looked along any of these axes, we would see exactly the same thing we saw with cyclopropane. But what actually happens here is that this folds a little bit. And we can see that here in this sort of three-dimensional perspective figure. We see the 3 points defining a plane, but then that 4th carbon is free to pucker, they call it, either up or down from the ring surface. And so when we look at the Newman projection, we have the Newman projection here, and one of those other 2 carbons are going to be in a plane. However, puckering that 4th one, it's drawn up here instead of down. It could be either direction, but puckering that reduces the energy of the molecule quite a bit. We can see we have now these hydrogens or these substituents, and the bonds are not quite eclipsed like they were in cyclopropane. So this might be more of that gauche kind of a conformation that we saw in the open chain alkanes when we looked at Newman projections in the first place. We can see over here too, we don't have any eclipsing of these bonds. And so we end up with a much lower total energy here because of that bending, because the molecule is able to twist a little bit. So we have reduced torsional strain here than it would have been if it was a flat square. And we have reduced steric strain because of the not eclipsed atoms. All right. Of course, as we get bigger, this gets even more flexible. The molecule gets even more, has more conformations available to it. The cyclopentane three-dimensional structure is often called an envelope. So if you can picture an envelope that you'd use to mail something, if you were to set it on the desk with the sort of flat bit of the envelope like this, the flap of the envelope would probably be sticking up like that, waiting to receive a letter, whatever you're mailing. That's kind of the conformation we're looking at here. So we have the 4 parts of the cyclopentane, these 4 carbons, not quite eclipsed with one another, not quite flat, because we only need 3 points to make a plane. And so if we look at our Newman projection, we'd have 1, 2, and 3, for instance, making that plane right here. But then we can have those other 2 that are out of that plane. And so again, we get a little bit further separation here than we had before, and much more separation than we would have had for the flat pentagon shape. So again, it doesn't matter which of these bonds you cite along. They're showing us citing along the 1-2 axis here, so we get our Newman projection like this, but we get a little bit of this stagger that's available to us. By the time we get up to cyclohexane, these are called chair conformations. And we're going to see that cyclohexane occupies two different, or has available two different types of conformation. We're going to see the chair conformation, and we're going to see a boat conformation. And so if you have a model kit, this is really helpful to build this molecule. Just connect 6 carbons in a hexagon shape. Connect some substituents to each one, so a couple of hydrogens. I like to color code one of them or a couple of them just so you can see what we're about to talk about here. You don't have to build out whole big functional groups, but color code something so you can see the difference. But when we talk about a chair conformation, you can sort of think about a chair like this very stylish chair here. If we had carbon, 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 sort of our 4 parts of the ring would make the seat of this chair. We'd have 1 carbon down here at sort of the footrest kind of position, and we'd have 1 carbon up here, the headrest kind of a position. Okay, and so this is sort of the chair conformation that we're going to talk about, where we have 4 carbons pretty much in a planar structure, and then we've got the other 2, 1 up and 1 down. This is the lowest energy version of this conformation, and I'm going to show these to you as we go forward. Okay, so this is the chair, this is the lowest energy conformation. There is also one called a boat conformation, and you'll see different words for different variations of this, but a boat or a twist boat are common ways to talk about it. And essentially, this is what happens if you take your model and move the footrest up here, or the headrest down, right? So we end up with something basically shaped like this. That's where we get that name boat. And we can look at that here on the next page. So at the top, we've got our chair conformation, and hopefully you can sort of see that chair version here in the skeletal structure that we're drawing. There's a model shown over here to the left where we talk about our seat being right here, our headrest going up like that, and our footrest going down. Now you should practice drawing these, okay? There are rules given to us in the book and on the next slide about how to draw chair conformations, but your best bet is to talk about drawing, let's pop ahead for 1 second, drawing the sort of seat part as 2 parallel lines, making a point up here roughly equal to the height of this other part of the seat, and drawing that point, and then drawing your 6th one, your last carbon, roughly equal to the bottom part of the seat, and drawing a point there. All right, ideally, you should have 3 sets of parallel lines when you're done. So the black ones shown there, the red ones, and the blue ones. It does take practice, but please, when you're doing it, don't, sort of compress yourself like this, right? That's bad. Try to really give yourself the space that you need to fit in whatever substituents it is that you're going to need to draw on this thing. And it can get crowdy, okay? So as you're drawing it, don't hesitate to sort of, oops, I drew that one in the wrong place. I don't know how to erase here, so forget this one, should have been there. So don't hesitate to draw yourself the picture, and if it's getting too crowded, just redraw it. Draw it a little bigger, whatever you need to do, okay? But if we were to look at that chair conformation, now you might notice here that as we're looking, we're going to look along both of these parallel lines at the same time. And so our Newman projection is going to actually have 2 Newman projections going on, connected to the front and to the back carbon like that. So this is my little happy face guy. I've got 1, 2, 3, back circle is 4, down here is 5, back circle is 6 carbons. And then of course my other substituents would look like this. And so you can see now in this conformation, I have nothing eclipsed at all. Everything is really well staggered. When I talk about the boat, now this is what happens when I bend that footrest that used to be down here. I bend that up towards the top, I do introduce some more steric strain because I have more atoms close to each other on this top side of the ring. You can see the twist here as well, and if you were to try to do a Newman projection, you'll see a little bit of eclipsing. So we have torsional strain, we have some more steric strain, and that ends up in the twist boat formation of being about 23 kilojoules per mole higher in energy. And so what does this mean to us? Well, 23 kilojoules is something, but it's not the end of the world. And if we have a sufficient amount of temperature, it means that we can actually have these things flip from one to the other. And so we can have a chair in one conformation that somebody could very quickly model like this. We could have it switch to being that twist boat kind of a formation like that. Terrible drawing, apologize. To one in which we have the other chair conformation. And this would be an interchangeable kind of a progression. So we need to think about where in space those substituents are going to be. We know the carbons are all going to be connected to one another, but we need to think about where in space these guys are going to be. And in that chair conformation, we're going to spend a fair amount of time on this conformation. So if you haven't modeled it yet, pause the video, grab your model kit, build one. We're going to talk about axial substituents. Those are ones that are either straight up from the ring or straight down from the ring. And you'll notice that they alternate as we go carbon to carbon. We have axial down and then up and then down and then up around the ring. Every carbon will also have an equatorial substituent, right? Because every carbon's got 4 bonds. And so 2 bonds are occupied in the ring. 1 bond is axial. The other bond will be equatorial. So if I look at that, this picture down at the bottom is just showing you all 6 equatorial substituents, but it's showing it on 3 different pictures, so you can see the opposing pairs. If we were to put them all on one, you'd see something like this. Okay. And so equatorial substituents are drawn up or down, but they're drawn at an angle. And so again, this is where the drawings can get messy if you're not careful. But what we'll see is that every carbon has an equatorial bond and an axial bond, and those point in opposite directions. Now, if we go to our three-dimensional model here on the left, you can see this red on this carbon. This red axial substituent is pointed up towards us on this picture. The blue equatorial one on the same carbon is pointed away from us. On the next carbon down, the axial position is pointed away, so we don't even see it. It's directly eclipsed back there behind this carbon. And then the equatorial one is coming up towards us. And we get the reverse and the reverse and the reverse. So when we think about drawing a flat hexagon picture of a cyclohexane ring, and we think about how every substituent has, or sorry, every carbon has 2 positions available to us. Basically, when we're drawing it, we can decide which ring conformation we're looking at, which chair we're looking at. We can say, okay, if that one is axial towards us, this one is equatorial away from us. And then on the next carbon, the axial was up here, and so the axial would have to be down here, and equatorial down on the first one, up on the second one. And again, and again, and again, and again. We can keep going around and around and around. When we do a ring flip, and that is when we go from one chair conformation, notice our footstool is down here, to the other chair conformation, footstool's up there. So we flipped through that boat conformation to the other stable chair conformation. And do this with your model. The way to do this with a model is to hold the 4 carbons that make up the seat, hold those steady in your hand, and physically pull the footrest carbon, the bottom one, up, and push the headrest carbon down. And you'll go from a picture like this on the left to a picture like that on the right. This process is called ring flipping. And what we'll see is that anything that had been axial will become equatorial, and anything that had been equatorial will become axial. Now, this picture in particular bothers me, all right, because they've done two things. They've done the ring flip, but they've also moved the position of these guys. All right, that one that I just dotted in red is the same carbon. So they ring flipped and they turned the drawing. You don't have to do that, but they did here, and I wanted to point that out. So notice here, any substituent that was above the ring to begin with, after you ring flip, that will still be above the ring. It just went from the axial up position to the equatorial up position. Anything that was down will remain down. It just goes from axial or equatorial down to the opposite, axial or equatorial, but still down. Okay, nothing crosses from the top to the bottom of the ring when you flip the chair conformation. And so when these are all hydrogens, of course, we don't have a tremendous amount of steric strain. Hydrogens are really tiny. So all we're really dealing with is the angle strain, which is the same between both molecules, both conformations, and the steric strain, torsional strain from the bonds, which is the same between both conformations, and so it makes no difference. So as long as we have enough energy to overcome that twist boat, that 23 kilojoules per mole barrier in between the two chair conformations, we can flip these back and forth with no problem. Now, as we start to add some substituents that aren't hydrogen, and bromine is used here just because it's pretty large, okay? We can see how that great big bromine could be here, and if we flip it, it would be there. Now notice what they did again. They flipped this from the axial position to the equatorial position. That's great. They also rotated this molecule as they drew it again, so that carbon with the bromine is now drawn here. Frankly, that's just because they use the same model. It's just a graphic laziness, but pay attention to what's going on here, okay? The only change is that we're going from axial to equatorial. Bromine was here, and it's here. It's still bromocyclohexane, same molecule, just two different conformations. These are not two different forms, okay? These are readily interchangeable back and forth. So in a given population, you would, if you could freeze them, and look at each conformation, look at all the molecules, you'd see both of these, all right? But the ratio of the two forms depends on that energy stuff that we've been talking about this whole time. So if we're talking about a monosubstituted cyclohexane, like that bromine that we just saw, or the methyl that we're seeing here, we need to think about what's around it. And typically what we'll see is that if a group, a substituent, is in the axial position, it will have more steric strain with the other axial substituents on its side of the ring than it would if it was in the equatorial position. And so these are called 1,3 diaxial interactions. Okay, whatever the naming is on the molecule, that doesn't matter. This is just saying the relative positioning is on carbons 1 and 3, whichever direction you choose to go. And that's because that's where the three axial positions are on the same side of the ring. Okay? So we have tabulated these. There is a table that you can find in the textbook. It's table 4.1. And that'll show you the relative energies that are involved with these diaxial interactions. And I'll show you that table in a minute. But what I want to show you here is the function of ring flipping this thing, okay? So if we talk about the molecule on the left, this is the one with the axial methyl group, we have to worry about these two diaxial interactions between methyl and hydrogen. And it turns out if we go and we look in that table that we're going to see in just a moment, each one of these costs us 3.8 kilojoules per mole. So that's 3.8, that's 3.8. And so this one has an added energy of 7.6 kilojoules per mole, just adding those together. Right. The hydrogen-hydrogen interactions are considered to be zero because that's as good as it can get. Yes, there is some steric interaction, but it's as good as we can get. Hydrogen's the smallest possible thing. In the equatorial version, after we've done the ring flip, okay, ring flip like this, after we've done the ring flip, that methyl group is out to the side. And if we were to think about a Newman projection along this axis, what we're going to see is that we have staggered interactions here. They're not eclipsed. So that equatorial up position here with the methyl group and the equatorial down on the next carbon with the hydrogen, those are not eclipsed. And so this is as good as it gets. We don't have anything extra. Our 1,3 diaxial interactions up here and down here are all hydrogens, and so those are zeros. And so when we compare these two molecules, we'd say the methyl one up top in the axial position is 7.6 kilojoules per mole higher in energy than the lower one. All right, so if a problem asks you which one is the higher energy conformation, this is how you'll do it. You'll calculate these diaxial interactions, and we'll come up with a number like this. Now, if we were so inclined, we could do some calculations to find out the percentages of these two and what we would expect if we could freeze time and look at all the molecules. But for most of the problems, we're just going to be looking at which one is higher or lower in energy and trying to explain why. All right, here's that table 4.1. I've written it for the PowerPoint, but here's our baseline. That's as good as we can get. And as the atoms or substituents get larger, we see this increase in diaxial strain. So this is for each hydrogen, notice. And so on our chair conformation, just like we did on the previous one, if I'm wondering about this guy, I have to think about its interaction with both, oh, not that one, sorry, it'd be here. Not that one, sorry, I don't know how to erase in PowerPoint. These two would be our 1,3 diaxial interactions. So I have to double the numbers that are found in here. So that's where I had 3.8 for my methyl group in the previous example. So it's methyl to hydrogen, 3.8 times 2 is 7.6. If I had an ethyl, it's a little bigger. If I had an isopropyl, it's a little bigger yet. A phenyl ring, even bigger, and then a T-butyl group is just disastrous. And so in general, we're going to say if we have the option to put a substituent in the equatorial position, that's better. That's the lower energy, it's easy. However, what if we have more than one substituent, right? What if I have a situation where I have a methyl group here and I have a chlorine here? All right, and I've drawn them both on the same side of the ring, but whichever the conformation and whatever the particular arrangement of these guys, we can model that out and we can figure out which chair conformation would be lower in energy. So before we get to the math, I want to look at this table. Please don't memorize this. Be ready to draw this, okay? Remember what I said. I'm going to draw a gigantic cyclohexane ring here so we have room, okay? Every carbon has an up and a down, right? We know that from the tetrahedral shape of these guys. Up and down, right? You get to decide on your little drawing. All right, let's say that I'm going to make this the axial position. All right, that means the down here, is axial, and the up here is axial. They alternate, right? Down is axial, up is axial, and down is axial. All right, and then likewise, of course, the other ones are equatorial. Equatorial here on a wedge, and here on a dash, and here on a wedge. And if I ring flipped this, that's fine. It doesn't matter. I'd get the same relative relationship. And so let's look at this. Now a cis 1, 2. Cis means they're on the same side. So for a cis 1, 2 disubstituted ring, I'd have one here and one here, right? Carbons 1 and 2, they're on the same side. And so I can see from my drawing that one of those will be axial and one will be equatorial. If I ring flipped it, it would be the other way around, but I'd still have one axial. The situation's different when I look at a 1,2 trans. Now that'd be the dashed bond here and the wedge bond here. In that case, I could have both axial, as I drew here, or both equatorial if I were to ring flip it. And notice that this pattern is different for each one, but if you draw this hexagon picture, so if you can draw this thing off to the side, then you can come up with this on your own. You can say, oh, 1,4 trans. Well, that'd be that one maybe is the up and then across. This one's the down. Oh, look, that's equatorial, equatorial, or axial, axial. When we have the opportunity and we do here and here and here. If we have the opportunity to put both substituents in the equatorial position, that is the lower energy for sure, compared to both being axial. We don't even have to do any calculation. However, in these other cases where one of our substituents will always be axial, we have to look at that table and figure out which one costs us less energy to put in that axial position. One of them has to be there. Which one is going to be better? And so as an example, right, if we look at this, here's a dimethyl. All right, now look at where our substituents are. I've got this one going up and this one going up. So that's a 1, 2, and that's a cis. Both are up. So the cis 1, 2. If I draw it in this conformation, my one is going to be axial. The other one is going to be equatorial. And so I'm going to count the energy for just the axial one right here. And so I have a gauche interaction between the two methyl groups. You can see that if we were to look at the Newman projection along here. And I've got two of these diaxial interactions with hydrogen. In the lower version down here, this is after a ring flip, we see that the red methyl group or pink methyl group that had been equatorial up is now axial up, and the methyl in blue that was axial up is now equatorial up. Remember, they're both still up because things don't switch from up to down when we ring flip. They just go from axial to equatorial. In this case, though, because these two substituents are the same, we end up with the same interactions. And so we have the two methyl hydrogen diaxial interactions, 7.6 kilojoules per mole total, and we have a gauche interaction between the two methyl groups that costs 3.8. You'll want to note that number, 3.8. That's not in the table because the table is on diaxial strains, so this one's buried in the text. So make a note of that one. Since these have the same total energy, there's no energy difference, and so we would expect a 50-50 mixture of these two forms. And of course, we can't tell the difference because they're exactly identical. However, if we were to radioactively label one of these or something, if we could tell the difference, we would see these two conformations. The story is a little bit different when we get to a trans molecule, because now when we talk about one of the conformations, we can have both of these guys, these substituents, in the equatorial positions. That costs us almost nothing, certainly no diaxial interactions. It does cost us that 3.8 for the gauche interaction between the two methyls. But when we ring flip it, we lose the gauche interaction, but now we have both methyl groups in the axial positions. And so we've got two of those 3.8 diaxial interactions up here in pink, and two additional ones down here. So 4 times 3.8 gives us over 15 kilojoules per mole. And so in this case, you'll see the equilibrium arrows here are disproportionate because our top conformation is lower in energy and so more common than our lower one. So if a problem were to ask you which of these is higher in energy, it'd be the bottom one. Lower in energy is the top one. If it asked which one is the more common or the majority conformation, the lower energy one will exist in the higher percentage. So this is the more common one up top. And we could do the same kind of a thing if you modeled out all of the other ones. If we look at 1,3 substituents, now here's our sort of model of the 1,3 substituents. And if we look at that table again, if we had cis 1,3, we can see a clear winner here, equatorial, equatorial. If we had 1,3 trans, we would have to draw out and figure out which one of the two substituents cost us more when it was in the equatorial position. All right. And so we'll see an example of that in just a minute. Questions might ask us if molecules are isomers of each other. Are they constitutional isomers or are they stereoisomers? So remember, constitutional isomers are those that have a different connection between atoms. So 2-bromopentane versus 3-bromopentane. It's all the same atoms, but I've moved one of the groups from one place to another. Stereoisomers are those that have all the basic connections the same, but the three-dimensionality has changed. And so here are two common molecules you'll hear about in biology, biochemistry, everywhere else, two hexo sugars, glucose on the left, mannose on the right. And the difference between them is highlighted here, that we have this OH group is in a different position. And so these two are stereoisomers of each other. The OH is still connected to that same carbon. However, it's moved from below the ring here to above the ring there. So stereoisomers of each other. So are they isomers? Yes. What kind? Stereoisomers. Which one is more strained? Well, remember, we want to look at the differences. All right, all of these interactions cost us something. Everything in black costs us something, but they're all the same. So we want to look at the change in pink. All right, this OH in mannose is on the axial bond, and so we'd have to worry about diaxial interactions, whereas in the equatorial version down here, it's not. And so mannose is our higher energy, not by much, but higher energy. And so here's a typical problem. Okay, draw the more stable conformation of this molecule. So you would draw this, right? We would say, here is my basic molecule, okay? Cis 1, 4, so there's 1 and 4, and I'm drawing both solid wedges because it's cis. Could have drawn dashes, doesn't matter, but as long as they're the same. T-butyl is our great big CCH33 group, and the other one is a chlorine. Okay, so now we want to think about this. All right, let's see. What if I put this in the equatorial position? Because I know that's low energy, so let's think about that. Then I know this hydrogen would have been equatorial because it's now, instead of up, it's down. All right, then this hydrogen would have been equatorial. And then this chlorine, well, this hydrogen would have been equatorial. All right, which means that chlorine would have been axial. So I see I'm going to have one axial and one equatorial substituent. So now I've got to think about, well, which one of these is going to cost me more when it's in the axial position? And when I go and I look at that table, I see that the chlorine diaxial cost was listed as 1 kilojoule per mole, whereas the T-butyl cost was listed at 11.4. Okay, so huge difference now. The more stable conformation, so what they're asking for, would be the one where I put the T-butyl group in the equatorial and the chlorine in the axial. All right, and to show that on the top here, that's this more stable here. Yes, I do have this cost, 1 and 1 for a total of 2 kilojoules per mole, whereas over here, I've got 11.4 and 11.4 for a total of 22.8. Right, so this is probably even a better way to draw that equilibrium. All right, so you can do this math from the flat structure if you remember to draw, or how to draw this little axial equatorial thing that I showed you. It's easier than trying to draw out the chairs, frankly. So if you can get used to doing it with the flat hexagon, that's great. If you need to, or if you're asked to draw the more stable like this one, you would do it this way, okay? So there's the math I just did. There's a little bit here at the end about polycyclics, and we're not going to talk a lot about polycyclic molecules, but I do want to just point out that when we start to introduce additional rigidity, okay, so decalin is a molecule with 10 carbons, so 6 here, 7, 8, 9, 10, but it exists as two 6-membered rings essentially fused together, and they're sharing 2 carbons right here, of course. If we have cis decalin, now this cis is talking about the relative position of these substituents on the bridgehead. Okay, if those are both pointed in the same direction, then these carbons have to be pointed in the same direction as well. And so if we had one ring like this, the other ring is going to look like that, right? This is axial up, This is equatorial up, like we know a cis 1, 2 should be. And so we can end up with the two rings essentially perpendicular to each other. Okay. If we were to talk about transdecalan, that would look like this. Now we know a trans 1, 2 is going to look like this. I've got one in the axial position there, one in the equatorial position there, and we'd have the two rings essentially side to side. And so instead of this kind of a structure, we get this kind of a structure. Put a little dot there so we can see the separation. These, of course, now these two rings being fused to each other, it does limit their flexibility a little bit, right? If I'm talking about trying to ring flip this, the ring on the right side, if I tried to ring flip it, now I've got to move all of this bulk down here. And so the more structural rigidity we have, the more decreased rotation we have. And so we get these radically different structures when we start talking about large molecules. And this is true then when you start looking at biochemical molecules like hormones that have a 4-ring fused system. We start to talk about things like DNA bases, the purine bases that have 2 rings fused together, all sorts of different examples where we have multiple rings fused together. The stereochemistry at those bridgehead carbons is critically important. All right, and with that, we are going to wrap this one up. Chapter 4, I really encourage you to get out your model kit and build some of these molecules, both the open chain alkanes as well as the ring structures. Go back and look at what a 3 and a 4 and a 5-membered ring would look like, but spend a lot of time on those 6-membered cyclohexane rings and looking at the chair and the boat and visualizing the ring flip. Spend some time now looking at how the model can help you visualize on paper, because there are going to be plenty of examples where you have to do this on paper without a model kit in your hand. So take this time to really develop those skills. Our next chapter deals with stereochemistry. That is going to be another visual one, so keep that model kit handy. But until then, that's going to wrap us for chapter 4. So email me if you have any questions, and otherwise have a wonderful day. Good luck.